Okay. Uh, how many of you went through the stuff that I just taught the previous class? Some of you. It's very important in physics, especially, that you just follow up and do a simple thing. That is, take your notes. You just did barely one page, right? And did you read through it? I mean, you should just go through it and say, all right, what did we discuss in the last class? Let me see if I am okay with it so far. And like this, you have to periodically check this and say, all right, I got this, and I got this. And after every day's class, whether you have a class or not, it should be a daily exercise of trying to find out what you have got on the notes. And your mind should be fresh with the knowledge all the time. Instead, if you just kind of take some notes, keep it away, take some extra notes, keep it away, take some more, and finally when I say, all right, we got a chapter 1 test, it'll be too late. Then you look at the whole thing and say, oh my, physics is tough, or the teacher is bad, I can't understand anything, that sort of feeling will come into you. So what's the solution? Solution is daily. Try to follow what we have done, and then just, you don't have to sit and learn so much, but just go through those pages and just become more and more familiar. Okay. Just like in sports, what do? Before a game, you do practice, right? It's the practice that makes you perfect. You might have played last year, and you know the game, but that doesn't mean that you can just be good at it. You need to practice and make sure you are aware of everything before you actually play the game. So that's why you have practices. The more you drill your mind with the material that you are actually learning on a day-to-day basis, you might have understood everything in class perfectly, but because you did not look at it again, it just slipped off. Your brain has two parts. Your brain has two parts. One is the RAM, and the other is the ROM. Just like your computers. Have you heard about RAM and ROM?
Yeah.
What is RAM?
Random access.
Random access memory. What is ROM? Read-only memory. Just like computers. Our brain is the best computer. So we do have a RAM. We do have a big ROM. The ROM is big. Now, which one is more important? The ROM or the RAM in a computer? RAM is very important because the processing, instant processing, will be better done when the RAM is good. Otherwise, it will be very slow, very, very slow. Now, sometimes you see, I can't play this video game on this computer because it's got a poor RAM, right? You need at least 8 GB or 16 GB of RAM to get it going fast. So we do have a RAM, and that's what is needed for you to process things instantly. That's an instant memory thing. It is not a permanent memory. Permanent memory is the other one, read-only memory. So if I ask you, what did you take for breakfast today in the morning? Are you able to recollect it? Easy, right? What if I ask you, what did you take yesterday? See? I can see some of you trying to fetch it. And then, what did you take on Saturday? What did you take on Friday? What did you take, the beginning of this week and so on? Last week? You'll be lost, totally lost. You're like, I don't know. Unless you eat the same thing every day, you won't be able to remember. You won't be able to remember what exactly is going on. What did you eat? Why? Because you don't care about it. Simple answer. We don't care about what we ate some of the day and all that because what's the point? There's no need for it. But is it needed? To some extent, yes, we need it. If someone says, what did you eat for breakfast? And you say, I don't know. That is terrible. That is bad. So you need to keep it somewhere. And the random access memory is something that you use it temporarily and then you throw it away. You don't want all those unwanted pieces of data. Now, if you want the piece of data, what do? You copy it into the ROM. You have to put it there. And once you put it there, it will stay forever. I mean, on the computers, of course, you can delete it, format it, and stuff like that. But I'm talking about a brain. If you manage to put it on the ROM, it is a permanent memory thing. You can only read it. You cannot erase it. Certain things that you remember of your childhood. Do you remember anything of your childhood? You cannot erase it. You try to forget it, you cannot forget it. The more you try to forget it, the more you actually recollect it again and again. It is there, stored up in huge terabytes. There are a lot of spaces there. You hardly use them. But you have plenty of space and plenty of RAM. You need to be able to process it and put it there. Same with any subject, physics or math or whatever. If you need something, you need something for future, put it there. Read-only memory, put it there. It's, aged people, they suffer from forgetfulness, right? Dementia. What is actually happening for them is that the RAM is getting affected. The RAM is not working as well as it should work, which means the processing is slow and it is not able to remember something that happened just like that. That's why some of the aged people will say, what's your name? And then you say, my name is this. And then 30 seconds after they'll say, what is your name? They'll repeat. Have you seen people like that? Loss of memory, instant. Ask them about their childhood. They'll bring out stories one by one. They have not. They will never forget it. That is the permanent one. That once they start telling that one, it will just flow like anything. Exactly the same thing. Have you seen people saying that? That exactly is what I'm trying to say. Now, how do you put things into the ROM? That is what you should understand now. How do you put it into the ROM? By continuously practicing or trying to do it over and over again, practicing more number of times. If it is a problem solving, you just don't solve a problem once and say, all right, I got it. You might have got it in class, but again, after a week, you look at it, oh, what is that? I don't know what to do. But instead, what do you do? Just flip through the pages, and then you'll see, oh, I got it. I got this. I have full control of the subject now. That is exactly what you do. Certain things get into your head without forcing it, and that's because just by practicing it. Do you remember the phone numbers of your parents by heart? Or do you have to look it up? By heart. Your house number by heart? Yeah. Address by heart? How did you sit down and say, oh, my house number is this, my house number is this, or my dad's telephone number? You didn't sit down and memorize it. It's just because you used it multiple times, you just got it. It goes with the ROM. So many things like that are sitting in your ROM right now because you just used it multiple times. Simple. You play a video game multiple times, you get better at it, and because you experience, and therefore you start doing good. Right? It is just a matter of practice. The same thing applies to even education. You cannot learn something once and then it will not stay. It might stay temporarily and it might just get wiped off. Because you know that I'm not going to use it. You're not going to use something so it goes on. Do you get it? Now sitting in your seat, I'm just telling you, if you just close your eyes, sitting in your seat, and just imagine you're walking into your house. Just imagine you're walking into your house, even with your eyes open. Just imagine you're walking into your house. You can literally see all the steps, the door, the doorknob. You enter and you see the floor. You see the poster sitting there. You see the couch. You see it all. It's like a movie. You can play it back like a movie. Yes or no? Everything literally is there, and you're seeing a video of it. And why is it sitting there? Because you just went that same path multiple times. All those things that were sitting on the way got into the ROM. It's not going to go away that easily. Even if you shift your houses, after 10 years after moving out from that house to some other house, you'll still be able to visit that house. Literally going into each and every room. Have you moved houses? Anyone? And if you've moved, you would have that experience. You can literally go here and there. Because it goes into your head. It's just going to permanent memory. It won't, yeah, yesterday I was like driving to Chicago. I didn't want to miss the mass, so we had to go for a function. So we just looked up for the mass timing, where, and then we got a certain church, a Catholic church, doing a mass at this particular time. So we just drove in straight there. It's a new church. Sat there, had mass, and then came out, drove. Now, the church and all that is kind of fresh in my head right now because it was only yesterday. I'm not going to remember all the details as to which place it was even after some time. No, it will just wipe off. It just is a, because I'm not practicing that again and again. I'm not going the same way again and again. So it will go away. Same thing you should do. I'm not going to take too much of your time, but that is what I want to insist. Go through it. Now, remember, without even opening your books, so keep your books closed. What is a physical quantity? Yes. Good. See? You bring it back. And that's exactly what you do when you read at home. Oh, something that you measure. And what are the two different kinds of them? Derived and basic. And basic, what is the meaning of basic? So this is basically how you kind of recollect. And if you had seen that page Saturday or Sunday once, it will come out. And after today's class, you will have 2 pages or 3 pages to look into. And you will be able to get more and more information, and everything should stay fresh in your head. You understand what I'm saying? All this I said mainly to make you understand that reading at least for 10 minutes for each subject is very important on a daily basis. Don't keep away something and keep piling stuff one on top of the other. It is bad. Okay? So let me start off that way. So physical quantities. Physical quantities are quantities that can be measured, and the 2 kinds of physical quantities . The 2 kinds of physical quantities, basic, and the other one is derived. Basic and derived physical quantities. And what is the meaning of basic? Exactly, a quantity that can stand alone. It doesn't require the support of any other measurement, right? That's a quantity that can stand alone. What is derived? It needs the support of multiple, 2 or more. It needs a support of 2 or more. Those are basic and derived. And I told you, derived, there are thousands of them. You can have thousands of them. You have volume, you have area, you have speed, you have pressure. And like this, there are so many. You cannot study everything and memorize everything. As we go through one topic to the next topic, you will be introduced to new derived quantities. Basic quantities are limited. Did we finish all of it? The list? The most important of those basic, length. Right? Length is the very basic one. To measure something, yeah. The length is a very basic quantity. It's a standalone quantity. And then comes mass. That is also another standalone quantity which is very basic, and it goes into every topic. Next one is time. These 3 are very important. Apart from these, then comes temperature. We have temperature. We have electric current. And we have light intensity. And we have quantity of substance. Have you got them? What was the last one? Angle. Also, although angle is actually not, angle doesn't have a proper, it's neither there or here, but still we put it on this side. Anyway, angle. These are the basics. That's it. No more. Any other quantity that comes your way is going to be on that side. Any other quantity comes to your knowledge as we go on from topic to topic will go on that side. Density, acceleration, so many things. Now, to measure these quantities, we need the support of a number and a standard. We talked about the standard. You need something to measure. You can't just like blindly say, all right, I want 10 of them. 10 what? You need to know how many of what. Say, for example, over here, the length of this room from here to there, I can say 17 shoe sizes. So 17 is the number, and shoe sizes is what we call as a standard or a unit. So any physical quantity should be expressed in terms of a number and a unit. It's a product of a number and a unit. You can see, like the length from here to there is 17 shoe sizes. Make sense? Your mass is, say, 155 pounds. What do you mean by 150? That means basically it's 155 times 1 pound. What does that mean? That means your mass is like this. You put a pound on a scale. You put that 155 times. Right? So 1 pound, second pound, third pound, 155. That's my mass. You get it? So your mass is 155 pounds. And the pound becomes a unit. So it's a product. It's a product of two things, a number and a unit. Now, units. I'm going to focus now on that unit. Units are standards. Standards have come and gone. People have used very crazy units in the past. Mostly, people in power, like kings, they impose the rule in the entire country and say, all right, everyone in this country will follow, take notes. Everyone in the country will follow this particular unit. Have you come across inches? Yeah, you still use it, right? Feet, yards, miles, furlong, so many chains. There are so many units that are actually used, that have been used because somebody said, oh, everybody should use this. But are they seriously, scientific? They're not scientific. They're not scientific. We just use this. And then everything started getting measured in that particular unit. They're not scientific units. Like, there were some kings who actually said the properties, the land and all that should be measured in a unit called chains. So they actually literally had a chain with links. The links were the smaller unit, chains were the bigger units. So they'll say, all right, this side is so many chains and so many links. That side is so many chains and so many links. Nowadays we don't even use it. Right? Because it's not scientific. Because somebody said, okay, use this. Some people actually measure certain things like using elbow and the tip of the human finger. All right, 1, 2. And they may even give it a name. And that, of course, is not going to be a standard because it is your elbow. It's not going to be the same as everybody else's. So units have come and gone. So many units have come and gone. We are not going to worry. I mean, we're not going to really look into all those units which are totally meaningless and not scientific. You know what a yard is? What is a yard? Approximately 3 feet. Yeah. Yard is approximately from here to there. This is a yard. That's approximately 3 feet. And you know what a yard? I mean, how someone introduced a yard? Who brought this yard? Yard was initiated by a king in England, British. British king Henry, one of the numbers. There are so many kings. So King Henry, he actually wanted to impose his power on the people there. He said, all right, from now on, nobody uses any other units of measurement of length. I'm going to tell you which unit to use, and you should be following that. And guess what he did? He stretched out his right hand and told people to measure the distance from the tip of his nose to the tip of his thumb and call it a yard. And people just took a stick and measured it. The unit, yard, everything was measured in yards. That's how yard came. Is it scientific? Now, even after his death, they still have that yardstick as a reference, and then still they use. Don't we use it now? Yeah. We still hang on to it. We're still using it. Okay, on a football field, you can use it. It is not going to be, even if it is not scientific, it's okay as a measurement. But can you use it for measuring, stuff which are more scientific? It's not supposed to be used, but we still use it. Suppose you're pouring some concrete somewhere, they bring it in cubic yards, even today. If you order concrete, they'll bring it in cubic yards. Units, they're not scientific. Now, why scientific? Why do you need to focus on scientific?
So then does that mean like feet and inches aren't scientific?
Nothing scientific, no. Feet, inches, they're not scientific. It must be somebody's feet. The word itself says that, right?
So only like meters and stuff like that?
Yeah. So scientific units, why scientific units? That's what I'm coming to. Why scientific? Why should we worry about units at all? The advantage of having a fixed system of units is this, that you design something in Germany and you can actually read that same design over here, and then you can translate it properly because numbers are actually there and the units are international. Or for example, you're going to learn here, after finishing your high school here, you're going to do your further studies in Russia or in some other place. You can't use some other units there, you'd be totally messed up, right? Imagine you study everything in one kind of unit and then you go there and say, I don't know anything about those units. It'll be a totally new learning experience. It is tough to work with other units when you are knowledgeable about it. So, keeping one standard units all over the globe has an advantage, has not one advantage, many advantages. One, you can integrate the knowledge from one country to the other country, and you can actually work as an engineer in Japan and still do everything right? Passing information from one country to the other country is easy scientifically. And the other thing is also between subjects. If you're doing a measurement in biology and then you want to kind of calculate it using some physics into it, you cannot just do it if the units are totally different. In biology, you use some other frog legs. So many frog leg units. And then you come to physics and I don't know what is frog legs. Right? So it can be total confusion. And therefore, between subjects, if you want integration, between countries, if you want integration, you need to have a system of units, and that is called systems international. In short, it's called SI units. Systems International Units. Now, this is the system of units that is followed everywhere on the globe currently. They don't use any other units other than these. You know, planes have crashed in the past because they were using different units. They were using different units because one guy is flying at 30,000 of his unit and this guy is flying at 25,000 of his unit. Apparently, both of them were exactly the same. In the past, I don't know, one of them was a Russian plane, I don't know what the other one. You heard about it? Yeah. Mid-air collision. Why? Because they both thought they were at different heights. So they both thought they were going like that. But the units were different. And so the numbers are different, but then since the units are different, the 30,000 of this country apparently matched with the 25,000 of this country, so they're both on track and they collided. So those kind of mistakes can come, and you need to be clear about it. So these days we have very systematic use of units and terminologies, everything the same way. Yeah. You go to any country, the runways are marked exactly the same way. The taxiing is marked exactly the same way. So, you know, someone flying from some other country coming to a place, what are these markings? You can get confused. But I'm not familiar with this. Which way do I go? And also the terminologies, like instead of saying A, B, C, D, S, and all those things, they'll say sugar, you know, S for sugar. Yeah, Juliet, Romeo, hotel.
Oh.
See, he's slightly on the flying side, so he knows exactly the names. They use the names because you don't want confusions, because slight confusion is enough. You can have problems. Like if I say S, it may sound like F on a radio. You understand what I'm saying? Or P, T, B, they all sound similar on a radio. And therefore they'll try to make it clear. What's for T?
Same.
So like that. Even numbers. They won't say 9, they'll say 9er. So what's the pressure? 2, 9er, 9er, 2. So 2 is easy to kind of hear. 9, something's like not clear. On a radio, I'm talking about now. Directly it may be different. But on a radio it is tough. Therefore they make sure that no mistakes at all required. So we need something systems international, and systems international units is what we are focusing right now. So we don't care about other units that are used. Alright? We don't care about the other units that are used. Now let's go to this. What is the SI unit? So I'm going to write down here SI units. Next to the basic quantity. So this is the basic quantity and this is the basic unit. So basic quantity and basic unit. And we're not going to talk about any other units other than SI. Well, can we use some of the others? Yes, we can. You can, but it's not scientific. So if you're trying to plug it into equations, hear me right. When you want to plug it into equations and do some calculations, it should be in this unit. If you're just trying to quote something to somebody, that's fine. You can use any unit you want. At what speed did you come in the morning on this road? I was driving at 35 miles per hour. That's fine, as long as you stop there. But you won't take that number and plug it into equations, then you cannot use that. You have to use other units. Okay? So what is the SI unit for length? This is what it is. What is it? Meter. So write down meter, and symbolically we write lowercase m. Symbolically we write lowercase m. You can make a new table if you want to. Make a new table instead of writing it in the same place so that you will be clear. So write down basic quantity and basic unit. And then we're going to write next to each other there. Mass. Grams used to be the just one step before, but now it is kilograms. And that is kg. Kilogram, kg. So the SI unit of mass is kilogram. So if someone asks me, what is my mass in SI units? It is 80 kilograms. You get it? But if they don't say SI units, I can tell in pounds. I can tell in any other units. Time. Seconds. Just a lowercase s. Those three are very basic. Meters, kilograms, and seconds will be coming everywhere in all the chapters. Temperature. What's the SI basic unit? Celsius apparently is not. It is Kelvin. Right, you can write it down. Kelvin, K. Capitalize K. You don't put a degree on it. It's only for Celsius we write degree Celsius, but for Kelvin, just write K. Now, why Kelvin and all that, we'll see more about it in the other chapters, in thermal physics, which we'll do later on. But I can tell you something very simple. Suppose you have two beakers. Suppose you have two beakers. You have to do a little bit of imagination. I use a marker for everything. So now the marker is beaker. What is inside here is ice cold water. What's the temperature of ice cold water in Celsius? What is it in Fahrenheit? What is ice cold water in Fahrenheit? 32. 32. That's the freezing point. So that's 0 degrees Celsius. In Celsius, it's 0 degrees Celsius, right? You understand? And this is boiling water. What's the temperature of boiling water?
100 degrees.
100 degrees Celsius. Is that clear so far? That is 0 degrees Celsius, and that's 100 degrees Celsius. I'm using the unit Celsius. Now I'm going to ask you two questions. One is a qualitative question. The next one is a quantitative question. You know the difference between qualitative and quantitative?
Yes.
Qualitative is just by words, but quantitative is by numbers. Okay? Now, first one, call it. Tell me.
0 degrees Celsius.
No.
Oh wait, are you?
No. My question is this. Is this hotter than this?
Yeah.
Yes. That's no doubt about it, right? Is this boiling water hotter than this ice cold water? Of course, yes. Qualitatively, you're fine. Now let's go quantitatively. You just now said this is hotter than this, right? Definitely a certain number of times. So how many times hotter is this compared to this?
100 times.
If you say 100 times, what is 100 times 0?
Oh, that's 0 again.
You see that? You're getting stuck there. We are not able to answer it quantitatively because we are using Celsius, which is not a scientific unit. Celsius was just calibrated, that's it. They said, let 0 degrees Celsius be for ice water mixture. Boom. It's kind of take it. So because of that, we don't know how to compare, like quantitatively. This is not 100 times this. Doesn't work. It's not. Now what if this was -1? If this was -1 and this is 100, you can't say, oh, this is negative 100 times hotter. That makes absolutely no sense. So simple things like that, you cannot say it right because Celsius is not a scientific scale. Right? That's why we have Kelvin. Lord Kelvin designed the scale in terms of energy. So energetically, the real number of times this is hotter than this is like a little more than 2 times. Boiling water is just barely little more than 2 times hotter. Oh no, not even 2 times. Less than 2 times, sorry. It's less than 2 times. Kind of 1.5 times. So we are saying 100 times. That's way off. So anyway, that's Kelvin. Electric current, what is it measured in?
That watts.
Watts is for power.
Ohms.
Ohms is for resistance.
Newton.
Huh?
Newton.
Newton is not electrical at all. Newton is for force, good. Electric, huh? Joules is for energy. We'll see all that in different chapters. Electric current is measured in what? Like, it takes so many
Oh, volts.
volts is for potential difference.
Then I don't know.
Watts for power.
Those are my
You're missing the main thing. You're all close, but you're not hitting that right word. And it is printed on every gadget. Oh, like for example, those sockets there are rated 15. What? What is it? What's if you draw current from there, how much current is going to flow? The unit is right there. Come on, put it out. Tell me anything other than watt or volt or
Oh, amps.
amps. There you go.
It's right there.
Capital A, that's it. 15 amps. Those are 15 amps rated. Have you come across this? Amps?
Yeah.
I'm not talking about the amplifier.
Briefly.
Yeah. Amps is like, okay, that takes a lot of amps. Too much current. Ampere rating. So if you have any gadget that you're going to plug in, check behind, you'll see like how many amps it's going to draw. It'll say that. Amps. Light intensity is measured in a unit called candela. And CD. It is derived from the word candle. So how bright something is, how much is the brightness that's coming out of your hands. That. So that's candela. Quantity of substance, you must have done it in chemistry last year. How do you measure this much of gas, this much of? You have done it. It's just that you're not recollecting it.
Yeah.
You've seen that? Mole?
Yeah.
So you take 2 moles of carbon dioxide, and you take so many moles of nitrogen, things like that. Quantity of substance. That is moles. Angle. Degrees, again, is not scientific. Doesn't make sense at all to say 90. Somebody said, oh, let it be 90 degrees, so I'll be able to split it nicely into 30s and 60s and 45s, and So they just created that angle of 90. So we say 90, 180, 270, 360. Now if that person actually had said, oh, let it be 100. So it'll be 100, 200, 300, 400. It's not scientific. There's no definition for angle. There's no definition for a degree. It's just that somebody said, let it be 90, that's it. We take it. What is it?
Is it like DMS or something?
Say it again?
DMS. It's something I learned.
No, DMS is for degrees, minutes, and seconds.
Okay.
No, not that. It's very close. That's easy. And you all know this as well. You know it. Rad, radians. You have it on your calculator. You can set your calculator now. Pull out your calculators. We will be working with the calculators now. Now, if you press the mode button, the third line will tell you degrees and radians. Can you see that?
Oh, dang.
You see that, radians?
Oh,
Yeah, mine's already set to radio.
Oh, by default, it automatically goes to radians. But at a later time, I will teach you a little bit of trigonometry because we need a little trigonometry to work through physics problems. How many of you have done trigonometry? Probably not. I'll teach you the basics. The very basics, I'll teach you that and I'll make you use it.
is trigonometry like sine, tan, and cos?
Yeah.
Oh, okay.
You done some?
I think I've done
Okay. So I will teach you that in case you don't have any idea. I'll teach you that, and it'll definitely benefit you for future. But when I teach you that, if you're going to use sine, tan, and cos, and if your angle is in degrees, like 30, 60, 90 degrees, then you should make sure the calculator is put into the degree. If you put in radian mode and punch the buttons, everything that it spits out will be wrong. So that is something that you should be careful with the calculator. Okay? So radian is systems international unit. So that's it. Meters, kilograms, seconds, Kelvin, ampere, candela, moles, radians. Light intensity. You understand? Candela is a unit? Forget about it from now on. Because we are not going to deal with that chapter where we use this. In these 2 years, you're not going to basically do a chapter on light intensity. And so the use of candela is not a very common use at all, right? So just ignore it. Just forget about it. But when I say forget about it, don't erase it from your book, because yes, it is a basic unit. It is a basic quantity, but just make sure that, okay, now I have only the other ones to play with. Now when is this going to come in? It's going to come in thermal physics, automatically. Yeah.
Will that be light intensity? Will that be on the test or
No.
anything? Okay. So just know that it's a basic unit.
It is a basic unit, basic quantity, that's it. I'm not going to bring it in anywhere. Okay. Well, if I just ask you what is light intensity, is it basic quantity or derived quantity, then you can say yes, basic. Because you know the knowledge. I'm not telling you to wipe that knowledge out completely, but keep it on the page. When you do electricity, then you'll come across ampere. Until then, you won't touch it. When you do gases and stuff like that, that's when you will be touching on that more. So these will go subject, topic specific. But these three, meters, kilograms, and seconds, will go all over the place. That's why I said these are the most important of all the basic ones, out of all this. Now you will see only Kelvin in thermal physics. You will do ampere in electricity. You will do moles when you talk about gases, maybe some in atomic physics. Radian when you're talking about rotations and stuff like that, right? When you have to know about angles. Any questions so far? Any questions on this so far? So, length is measured in meters. So volume should be what unit? What should be the unit of volume? Huh? Meter cube. Perfect. Meter cube. Cubic meter. So we scientifically, cubic meter cube is the correct unit for volume. Not cubic yards, not cubic centimeter, not cubic liters, not cubic feet, not cubic any distance measure. Area should be what? Meter square, because there are two lengths that are going to be involved, so that is meter square. Speed. What is the SI unit? We are talking about SI units, okay? This is all SI.
Of meters per second.
Meters per second. Good. You know, it is not kilometers per hour or miles per hour or feet per second. It is meters per second, the SI unit. Can you use miles per hour? Yeah, you can always use miles per hour as a way of telling somebody that's it. How fast did you drive? Okay, so many miles per hour. That's it. But if you want to substitute stuff into your calculations, you should definitely put it down in meters per second. And I'll show you how to convert from one to the other and all that. So, all the derived units will have a combination of these basic units. Alright. Let me ask you a couple of questions. Any questions from your side?
What would pressures be?
Oh, pressure is a very complicated one because you're not studied pressure yet. That's why you won't understand what I write over there. So I'm not writing it.
What is it?
I can write it down. It is kilogram meter to the power of -1. You know, seconds to the power of -2. So it's a kind of, that's why I said it's kind of complicated for you to understand it, but leave it for the time being. Oh, this is, oh, pressure. Pressure is going to be what? Yeah, that's right. That's right. Yeah,
What is weight?
weight is force. So when you talk about force, weight, they're all identical. This is force. Kilogram, meter, second to the power of -2. Meter, when I say meter, it's only the power of 1. And you'll see them. As we go on, we'll see why is that unit? Why is that unit? Yeah. Now, instead of writing all this, we end up writing simply newtons. Shortcut. We write newtons as a shortcut. Instead of writing all this, we have letters to say what it is for pressure. You don't write all this all the time. But if somebody's asking you, okay, tell me what are the basic units of pressure, then this is what it is. And for pressure, you can always write Pascal. Have you heard about the word, the unit Pascal? That's the unit for pressure. So somebody says, what's the pressure in this room? And I'll say so many pascals. I won't say so many kilogram per meter per second squared. It's easier to say Pascal. All right, any other questions? So, do you know clearly the difference between quantity and unit? If I tell you something, will you be able to say, is it a quantity or a unit? Can you do that? Okay, here it is. Liters. Tell me, is it a quantity or a unit? Is it a quantity? It's a unit because you measure something in liters. You understand what I'm saying?
Yeah.
You measure something in quantity. I mean, a quantity is something that can be measured. And in what units you're going to measure, that's a different thing. So liter is actually a unit. Now, is it a basic unit or a derived unit? Liter is a basic unit. No, remember, basic units are very limited. Automatically it is derived. So, you know it's a unit and you know it's derived. Now my next question, is it SI unit or non-SI? It's a non-SI because SI unit of volume is meter cube and liter is also for volume. You understand? Same as gallon. What's a gallon? It's a unit. So make sure you're getting connections between all this. Gallon is a unit. It's not a quantity. And is it an SI unit? No. It's not an SI unit. It's a derived unit, but it's not an SI unit. So you should be able to differentiate between quantity and unit. And then you should be able to say, is it basic quantity or basic unit? I mean, derived quantity. Right? And you should be able to say, what is it? Is it a basic unit or a derived unit? So differentiate between basic and derived, quantity and unit, all of them, and SI. Is that clear? Let's go to scientific notations. Some of these things you have done in the past, so probably it is just a recollection, but I don't want to take risks of, they must be knowing it. What's a scientific notation? Have you come across it? What is it?
Smaller form of like a large number or
Exactly. Exactly. Good. Like if there's a huge number, you don't want to write all that down. You just make it into scientific notation so it'll be easier to read. Suppose this number is very small. Instead of saying 0.000000000 something, instead of that, you write in scientific notations. It becomes easier to read, easier to transfer information. It becomes easier. And even if some trivial mistakes, or if you knock off some of the digits from the numbers, it may not seriously affect your value. So I'll show you some example here. Let's say, for example, you won a lottery for this amount. You won a lottery for this amount. Right? You won a lottery for that amount. How much is this amount? 5 million. Yeah, it's $5,672,251.
$400.
There's plenty. You don't have to work for a lifetime. All right. So that's a lottery you got in, and then you went to the bank. The cashier was writing a check for you. You're going to get the money. But while writing the check, the cashier accidentally forgets to write 2 2s. Instead, only uses 1 2. And so the number on the check becomes this. Will you say, it's a trivial mistake, it's okay? Will you take it? Why? Because you're losing a lot. Look at that. What you're going to end up having is 567,251, not 5 million.
That's really what you get.
So you see, a little mistake in one digit has so much value. Oh, not only this, if the 1 is not written down. So you're getting 567,000. That's a big mistake. You can't just tolerate that. But if the same thing is written in scientific notations, have a look at it. If the same thing is written in scientific notations, now what is the scientific notation? You must be familiar, but anyway, if this is written in scientific notations, it will come out like that. A digit, decimal, the rest of the digits, times 10 to the power of a number. And then obviously, if the decimal is going to come here, from here, if the decimal is going to jump backward 1, 2, 3, 4, 5, 6 times, you need to make it appear as a positive power. So 10 power 6. That's called scientific notation. Advantage of writing scientific notation is that, let's say, when the person is writing this check in scientific notations, suppose did not write this 1. Forgot to write that 1. How much are you getting now? $1 less. You're still getting 5.67 something million. This is a million. So you don't have to have that 1 there. What about the 5 and the 1 missing? It's only $51. See? The significance, the importance of these digits is very clearly seen when you write in scientific notations. 51. $251. Is it okay to just forget about $251 when you're getting 5.67 millions? Yeah? $2,251, let go. Tips. When you're getting 5.67 millions, and that too freely, by luck. Let somebody also enjoy a little bit. $2,251. If you're so stingy about that last dollar, that'll be that. So 5.67 millions. Easy to read that number, right? Instead of saying all these things and making mistakes. See, it's very easy to make mistakes these days, especially when you're looking at a credit card and you're trying to write that credit card number online. Like you're pressing. There's a chance that you make a mistake, right? Because there's so many digits, and you may look at the same digit over and again, or you can just skip one. And so there is a chance that you make mistakes. But once it is written in scientific notations, less likely to make mistakes. So it's easy to transfer the information. So how much is the measurement? 5.67 millions. Very close. Not exactly to the dollar, but I'm very close. 5.67 millions. That is called scientific notation. How do you work the scientific notation on your calculator? I'll show you this. First of all, type this number 5672251 on your calculator. Just type it. How many of you don't have calculators here? How many? Why?
Mine's in my locker.
Yeah, mine's in my backpack.
Oof. So when are you going to do the Trinity thing before entering this room? 3 things. Your notes, your textbook, your calculator. These are 3 important things. Pencil, if you don't have pencil, you can collect the pencil here, no problems. But these are the 3 things that are important when you come here. You're going to use this plenty and you learn a lot. Now for today, again, I'm not taking off any grades and all those things. I don't like doing that, but it should be your interest to pull out. So sit with somebody else who has a calculator so that you don't miss anything. All right, type in this number 5672251 on your calculator. Press enter. All right, so you have that number, right? Now, how do you change it into scientific notation is what I'm going to teach you now. Press the mode button. And you'll see on the first line, it says normal. On the first line, it says normal. And then the second one says SCI. So scoot to the right to SCI. Have you done it? Then press enter. Clear screen. Enter again. Press enter, clear screen, enter. What do you see?
5.67225.
You will get this.
E6.
And then E6.
Is E6 like times 10?
Exactly. The E6 is the way your calculator is trying to tell you times 10 to the power of 6. It's basically what it is. Are you able to see that now? Good. Now, as I said, you can't be writing all the digits for every calculation. You need to chop it down and round it. Have you learned rounding? I'll teach you how to do it on the calculator. Suppose this is not the way you want to write the answers down. Press the mode button again. Press the mode button once and you see the second line. What does it say? So on the second line. Float. It says float on the second line. And float simply means how many decimal places you're looking for. Suppose I want 2 decimal places, I want like 5.67. I don't want the rest of it. Then what you do is go down to float and go to 2 because you want 2 decimal places, which is basically 3 sig figs. It's rounding up. So go to the right, go to 2, enter, clear screen, enter. And you see how beautifully the number is seen. The number will come out rounded properly to 5.67 E6. Easy to say, easy to transfer, no mistakes, less mistakes, or whatever. So that's what. So you learn 2 things: how to make it into scientific notations, and also how to round it off. Now, suppose you say, "Oh, I don't want 2 decimal places. I want 3 decimal places." Go back to mode again. Go back to mode. Go to a float again, and go to 3. No, float. Second one. Go to 3. Enter. Clear screen. Enter. Right? Now you have 3 decimal places. And suppose you say, "Oh well, I want only 1 decimal place." Go back again. Mode. Mode. Go to 1. Enter. Clear screen. Enter. See that operation. Enter. Clear screen. Enter. What do you have? 5.7. It is doing the rounding for you. You know the rounding principles. Like, if this digit is more than 5 and all that, right? If it's 5 or above, this will become 1 more. So it's done already. So in 1 decimal place, this is 5.7 E6. Very easy to round numbers. Very easy to express it. And calling it out, easy. 5.66 E6 basically means 5.66 times 10 to the power of 6. This format is very useful in future. I'll give you a simple example, and just to remind you of possible mistakes. You're going to do this work. Do this calculation. 9.57 times 10 to the power of 5 divided by 5.31 times 10 to the power of minus 7. Can you do it on the calculator and let me know what you got? Do it on the calculator and tell me what your answer is. Do it on the calculator and tell me what you have as the answer.
(1.8) E12.
1.12. Let's see. Oh, make it into two decimal places. Right. Oh, 1.80. All right. Got the answer? How much do you have? Can you read out your answers?
1.80 times 10 to the negative second.
Negative second.
Same thing.
Same thing. What do you have there? 1.8 10 power negative?
Yeah.
2. What do you have there? Same thing?
I got
Error? That's... Now, how many of you got 1.80 times 10 to the power of 12? Only one. That is the answer. Now, what went wrong? Use the same calculators. Use the same numbers. But what happened was there was a lack of communication between you and the calculator. The calculator will misunderstand you so quickly. So unless you tell it clear directions. So what the calculator did was this. You fed this number into it, and then you put divide sign, and you put this number. Immediately as you put this number, it already did the calculation. And then you said times 10 power negative 7, so it multiplied it instead of dividing. So what do? You put parentheses here. You don't have to put parentheses on the top, but yes. So to tell the calculator, see, everything that I'm putting under inside the parentheses is one thing. Then it will do it right. I'll show you how to do it even without putting parentheses. So what I'm trying to say is this. 10 divided by 2 times 5. Now without using calculators, tell me what the answer is. Without using calculators. 1. Now guess what will happen if you use calculators for this without parentheses? 10 divided by 2. Immediately it will calculate the answer is 5.
25.
And then times 5, 25. You understand the mistake? So it's not your use of calculators that is important. You should use it right. The communication between you and the calculator should go right. Yes.
So should the right answer be?
1.80 10 power 12.
Okay, that's what I got with the parentheses.
So if you put parentheses, you will get. Now I'll show you a way to do it in a much safer way. See, complications come only when you bring this multiplication sign. So instead of bringing the multiplication sign, you can use the E. So it will always take it together. Use the E. So if I'm going to do this calculation, without even parentheses, I'll do this. 9.57 E5 divided by 5.31 E minus 7.
Where's the E on the calculator?
Alright, the E is second function, comma. Can you see that E? There. Over the comma, you see
Okay.
W. That. Now, can you type in exactly as it is? Now, the minus sign, this minus sign on the calculator is a minus sign at the very bottom,
Yeah, number 3.
under the 3. The minus sign in parentheses, that's the minus sign you should use there. Type in this.
1.80 E12.
That's right. See, no parentheses used and less buttons punched. Second function, comma. Second function. Okay. And then you put and then divide sign. No parentheses required.
Blue button and then pop.
So got to practice these things, and then you see how things become easier. Now, how did you do earlier? You were doing like 9.57. You press the multiplication sign, and then you type in 10, and then you type in the power of 5. After doing everything, finally, you end up getting a wrong answer because you didn't put parentheses. So, you must have pressed it off. Oh, you have to press this minus. Yeah, the minus sign is supposed to be the bottom minus sign. So, when you press the minus sign, it should be this one, not this minus sign. Yeah, the white button. And any complicated calculation, you should be able to do it now. If there are two of these things in the bottom, yeah, it's better you put parentheses. If there are more of them, more complications. And suppose you want to do this. Suppose you want to do this. Absolutely nothing. You just type the same thing and put square. You don't need to do anything. If you want to do this squaring function, you just put 5.31 e minus 7 squared. It'll do it right. Check it up and see.
Oh yeah.
Right? It'll do it right. So that is kind of scientific notations, and you must know like how important scientific notations are and what's the purpose of scientific notations. I gave you all that idea now.